started. I have my oldest son, Benjamin. Can you wave your hand? He's here with us today. He is in the middle of midterms in high school and doesn't have class today, so he is going to be my assistant in a project that we worked on together. So, motion in two dimensions. So suppose we have, what we're going to do is we're going to draw a coordinate system. Once again, we're going to call this the y-axis. We're going to call this the x-axis. And now, what we're going to do is we're going to define vectors in this two-dimensional space that allow us to describe two-dimensional motion. So let's say, for example, I have a vector here, R1. Now, what is R1? That is simply the vector associated with the displacement of whatever we're watching at this point relative to the origin. So, for example, if I just want to look at the motion of this chalk, I may say, at time t1, I have the displacement of the chalk at this point relative to the origin. Okay, so we say at time t1, the chalk is here. Okay, and then at some later time, what I can say, the chalk may be up here. Okay? So all I've said is there is a displacement associated with this chalk at time t2, and there's a displacement of this chalk at time t1. And now what we're interested in finding is what got us from R1 to R2. And we want to think about this in terms of displacement. Okay? So what do we need to do in order to go from R1 to R2 in terms of vectors? Okay, good. So we make a vector from the tip of R1, we put its tail here, and then we put its tip up here. Okay? Now, we're going to call this delta R, which means that it is the change in the position of R. Now, we all know how to do this. We've looked at the summing of algebraic sum of vectors now, and we know that what do I need to do to get to R2? We're basically going along R1 and the delta R in terms of an algebraic sum. I need to say R1 plus delta R is equal to R2, right? Because if I have this vector and this vector, then I get this vector, right? I've added these tip to tail here, and then I said the resultant vector is R2. Well, now I can just see here, we're just going to use algebra here, and we can see that this implies that delta R is R2 minus R1. Right? All I did is I brought this R1 to this other side. And so now I can see that delta R, or this displacement vector associated with the change in the position of this piece of chalk from position 1 to position 2 is just delta R, and that's simply going to be given by R2 minus R1. So we're familiar with how to do that as well, and we could look at that. We could say, if I were to just draw delta R from out here, and then go R2, and then minus R1, that would give me delta R. Okay? If we think about it that way. So if I just simply draw delta R right here, Right? If I take this vector, bring it back down to the origin, and then I said, go out to R2, which is what this says, and then I subtract R1, which is this one. That gets me back to where I was. So any way we want to think about this, this is how we can write this. So delta R is literally the change in R2 minus R1. Now, if I were to look at this, and I say, okay, what is the component of R1 along the x-axis? We call that x1. And I'm just going to draw that out here for a moment. So x1 is the component of R1 along the x-axis. And what is delta R? Well, it's what we would call, it's the component here, you can see, the component of delta R along the x-axis, and that's this. And we're going to call that delta x1. And then you can see that R2, if I were to take the component of R2 along the x-axis, it is simply the sum of x1 plus delta x1. And so you can see that if I want to find what delta x1 is, I simply take x2 and subtract x1 from it. Similarly, I can do it along the y-axis. I can find this component along the y-axis for R1 as being y1, the component for delta R being delta x1, and the component for R2 being like this. And so we can see that the delta y2 is simply just greater than the y2 minus y1. Okay, so now let's write what R1 is. So in the vector notation that we're using here, we say that R1 is equal to x1 I hat plus y1 j hat. And that R2 is equal to x2 I hat plus y2 j hat. So what is delta R then? Writing it in this notation. Sorry? Okay, good. So basically delta R, as we were pointing out, is R2 minus R1, which is equal to, if I break this up, I have an x2 minus an x1 times I hat. So all I did is I bring everything together that has I hats, I bring everything together that has j hats, and I did x2 minus x1 I hat plus a y2 minus y1 j hat. So that's how we write delta R. Okay, so what is the magnitude of delta R then? Yeah.
The square root of x2 minus x1 squared plus y2 minus y.
Excellent. Thank you. Now, if you think about it from a triangle perspective, with delta R, all we're saying is, what is the component along the x-axis here? And we're squaring that. What is the component along the y-axis? Squaring that, summing them, and that gives me the length of that vector. Okay, so that's the magnitude associated with that vector. So if you want, one of the beautiful reasons about using orthogonal axes is we can use these right angle rules, and we can just simply break them up into simple components along axes that become essentially independent of each other. And this is the reason why we use orthogonal axes, and it makes our life simple when we use it in this way. Okay, so this is the magnitude of the vector, and then we know the direction simply by looking at the the components along here. And what we can do is if we want to find the angle, then we simply take the tangent of the opposite, which is going to be y2 over y1 over x2 minus x1. So if we're going to find the angle, then we just say so now we have both the direction and the magnitude of r, of delta r. Now let's do an example. Suppose we have a particle with x is equal to 3t and y is equal to 4t plus 3. All right, so what we have is we have a particle that's undergoing motion, and along the x direction, it's equal to 3t, and along the y direction, it's equal to 4t plus 3. So if I were to look at that, and I was simply to draw that out, at time t equals 0, what is this going to look like? X will be equal to 0, and y will be equal to 3. So we simply we go 1. At time 0, we can see this has y is equal to 3, and x is equal to 0. And then at time t equals, I'm going to need a bigger graph here. Let me do this again. Okay, so we have this at time t equals 0. Time t equals 1, we'll just associate this with MKS units, meters, kilograms, seconds. So at 1 second, then we're going to have x is equal to 3. So we go out to 3, and y is equal to 7. So we go 3, and then over 3, and then up 7. Then we draw our next point. Okay, at t equals 2, x is equal to 6. And this is equal to 11. So we go up to so what we can see is that we have a coordinate system where the displacement is moving away or is moving up linearly in this fashion. So if I were to look at the vector at time t equals 0, I could call that r0. And what would that vector look like? What would I call r0? Well, r0 would come up like this, right? What would r1 look like? And when I say r1, I mean the vector associated with the displacement at time 1 second. It's going to go from the origin up to here like this, right? And at time t equals 2 seconds, I'm going to get the displacement vector that looks like this. Okay, so if I were to look at this delta r, here's delta r over this interval, and here's delta r over this interval. Okay, so if I look at delta r over this interval or delta r over this interval, it turns out that they're the same since it's undergoing linear, since the velocity is constant. Okay. Okay, so let me just reiterate that. Delta r then becomes this change in what happened to the vector of what happened to the displacement as a function of time. And from time t equals 0 to time t equals 1 second, and then from time t equals 1 second to time t equals 2, it turns out that these are both the same. It's like saying, if I have this piece of chalk moving at a constant speed along this line, then if I were to look at a 1 second interval, every 1 second interval, it's going to move the same amount. It's going to propagate the same distance. Okay? Questions? All right, let's consider now. So this is basically all we've done is essentially a generalization of what we did with motion in one dimension, but now we've added the fact that this is actually propagating in 2 dimensions, and it's broken up into individual components associated with along one axis and associated along the other axis. You can think of this as one-dimensional motion along each one of these individual axes. If all I do is break up these vectors into components. Okay, so now velocity. So by definition, velocity average is simply the change, or this delta r that we've defined, over the time interval that the displacement occurred. So it had a displacement vector associated with delta r, but it took time delta t in order to undergo that displacement. So if I'm once again talking about this chalk, I move it from time at time t equals 0 to time t, it moved this distance, and so what I'm really interested in is the displacement and the time that it took to make that displacement. Okay, so this is the delta r over delta t, and we just use these definitions of what we've described in terms of this 2-dimensional component. Okay, so how am I going to write the instantaneous velocity? You with the red hair and beard. What do you think? Okay, good. So it's going to be dr dt. And what's your name? Brady. Brady. Braden or Brady? Brady. Brady. Thank you. So the instantaneous velocity is simply the change. If I were to have some sort of curve here, and I were to say, and what I'm really doing in here is, I have an R1, and I have, at some very close later time, I have an R2. Okay? And what I'm going to call this is VR, and what I've assumed by that is that this is, you can imagine that this is an extremely blown up, well this is actually delta R, right? So there's actually some curvature here, but if I were to make R2 very, 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 very close to R1, and this becomes a very good approximation if, for example, I make my time interval so small that the change in the velocity over that interval is essentially 0. Then what I'm doing is I'm finding that instantaneous velocity. And so if I take R2 to be some very, very close time interval a little bit later, it's just hard for me to draw this up on the board. But if I have R2 coming up like this, then I say that dr is that little tiny vector associated with going from R1 to R2. Okay, so, but what I've assumed is that the time interval is an extremely short time interval, so that I'm really looking at an instantaneous velocity. I'm sorry, this is such a small. I'm trying to point out when you ever draw infinitesimals, it's really hard to envision what an infinitesimal is when you're very far away from the blackboard. So Anyway, but the point is that this is for some extremely, very close displacement between R2 and R1. And this is the instantaneous velocity. All right. So if we go back to our example we had a moment ago. Okay, so if this is dr dt, then v is equal to d dt of the velocity vectors that we may have. For example, what we can just say this is r, which is, for example, so what we're just saying is that, sorry, I need a little vector here. So the velocity vector is the derivative of the position along each one of these individual axes. So I've actually drawn it for 3 dimensions up here. But if we have no movement out of the board, then we don't need to worry about this. But this is in general what we use. If I have a velocity, I have a vector, then I simply just say that the instantaneous velocity is the derivative of those individual components along the axes. Okay? And so what you can think about is this is undergoing one-dimensional motion, this is undergoing one-dimensional motion, this is undergoing one-dimensional motion. But when I bring them all together, I just need to bring them back into this coordinate form. Okay, so if I go back to this example here, what is the instantaneous velocity along the x-axis? Yes? 3, right? And the instantaneous velocity along the y-axis is just going to be 4. Okay? And using the MKS unit, this would be 3 meters per second, and this would be 4 meters per second. All right. Now, had this been a little bit more complicated than just saying that this is, say, 3t and 4t plus 3, I could have said that this is actually 4t plus 3 minus 11t squared, for example. And then I just need to remember that I need to take the derivative with respect to all of those individual things. So if this had a quadratic term or a cubic or a coordinate term, we just need to take the derivatives with respect to time for each one of those terms. All right. So now, let's see if I can cover everything there. Oh yeah, one last thing. So let's go back to this example here. So if I look at the velocity, I say that this is, in this particular term, okay, I'll do this example over here. So let's just do V average. V average is just going to be equal to the delta R over delta T. Now, we know that this is going to be x2 minus x1 I hat plus y2 minus y1 j hat all over change of time. All right, so we can define this as x2 and this x1. I mean, we can define this as R2 and this R1, or we can define this as R2 and R1. Or we can define this as R2 and we can define this as R1. Or we can do any point along here that we're interested in, as long as it's along this line and we know what times those are associated with. But let's just for a moment consider this to be time t equals 1, and this time to be time t equals 2. Okay, this is just arbitrary choice that we're making here. We're going to associate this with t1, and t1, and we can just say at time t1 we'll call that 0, and at time t2 we're going to call that 1. Okay? And what is x2 at this point? x2 at time t1, sorry, x2 at what this position we're calling t2 was, you recall that was associated with 1 second. And so the position was 3, right? And the position was here, 7, right? So then that means we have x2 at that point is 3, and x1, our time at this initial time here, x0 or x1 is equal to 0. And y2 is, at this point, was 7. And at this point was 3. And the total time interval was 1 second. Okay, so we get 3i plus 4j. And what this is literally saying is this is, I should put some units here. We'll just put meters per second. Okay. Because the top line are these are displacements which are in meters, and the bottom is in time. And so we get this meters per second. So we get 3 meters per second along the x-axis and 4 meters per second along the y-axis. Okay, so what is the magnitude of the velocity here? 5, right? This is a 3, 4, 5 triangle. Right, so if I take 3 squared, which is 9, plus 4 squared, which is 16, and then I sum those, I get 25, and I take the square root, and I get 5. Okay, so the magnitude of that velocity is 5. And what's the angle? How would we find that? So literally what I'm asking is, if I were to look at this displacement vector, it comes out like this. Okay? And now I'm asking, this is my total velocity. Sorry, what I'm drawing up here is my total component of my velocity vector. I have a component that goes out 3 units in x and 4 units in y. So this is 3, and this is 4. And how do I find the angle? Okay, good. So I take the arc tangent of 4/3, which is equal to 53 degrees. Okay. So 53 degrees is the angle of this velocity vector. All right. So now let's do average acceleration. So how do you suppose we're going to do average acceleration? Yeah.
Velocity 2 minus velocity 1 divided by velocity.
Okay, good. So we have, so this is a vector again. What we're going to have is velocity 2 minus velocity 1 all over the change in time. Okay? And we refer to this as dv delta v delta t. Now, in this particular example of x is equal to 3t and y is equal to 4t plus 3, what is the average acceleration? 0. Why is it 0? Okay, good. So the velocity isn't changing as a function of time. So this shows a trajectory here for example, if I were to launch a projectile, I would say that here's my initial velocity in the x direction, here's my initial velocity in the y direction, but that velocity isn't changing as a function of time. In this particular definition, x is always 3 meters per second, v of x is always 3 meters per second, and v of y is always 4 meters per second. And so neither one of those changing, and so the acceleration, the change in the velocity, in that particular case, is 0. Okay? If, on the other hand, I had said that y is equal to 4t plus 3 plus t squared, right, then I would have an acceleration because I would take the derivative of y with respect to t. And this vector. So, and then a, when we don't put anything down here in the subscript, we just mean that this is the instantaneous acceleration. And how do we find instantaneous acceleration? dv dt. Or the derivative in the velocity as a function of time. Okay. And we all know how to take rid of this. So we just need to know what the functional form of these are, and then we can find it. So if we say this, then we say this is ddt of, for example, dx dt plus dy dt plus dz dt a hat. And this is just going to be equal to the second derivative of x with respect to time, I hat, plus the second derivative of y with respect to t, j hat, plus the second derivative of z with respect to t, j hat. Or I can think about this. This is just the velocity along the x, the velocity along the y, the velocity along the t. So I can just take dv x dt I hat plus dv y dt j hat plus dv z dt k hat. Fantastico. Once again, returning to our simple example, you can see that if we take the second derivative of this with respect to t, it's 0. So that means we need to have something to at least, for example, if we're dealing with powers of t, we need to have something in second order in order to see something. I should say whole number of powers of t. Now for the fun part of this, which I think is quite fun. That is with projectile motion. Any questions so far before we move on? Everyone's happy? Yeah? You better? I need someone to do some push-ups up here to get us all excited again. Does anyone do some push-ups? Okay. I need to learn magic tricks or something like this. Okay, so projectile motion. So, what we have in projectile motion is what we're going to say is that there's some object. What we're going to say is it starts at the origin and it has some initial velocity coming out of here, which we're just going to call v0. And then the actual trajectory of this is going to come out and come like this. Now, when we talk about projectile motion, we're talking about the motion that an object experiences due to a uniform gravitational field. And so, obviously, due to this uniform gravitational field, it's just going to undergo what we call a parabolic trajectory. So if I launch something, if I throw some object, then I want to look at the projectile motion of that object. Now, in this particular case, this would not obey these equations, for example, because in projectile motion, while there is no force along the horizontal axis, well, there is, it's wind resistance, but we're going to ignore wind resistance. There is no force along the horizontal axis. There is a force along the vertical axis, and these act and behave independently of each other. So, if I were to now break this up, so what I want to do is I want to say, so V0 is going to be broken up into a component, which is V0x I hat and V0y j hat. So all we're doing is we're saying this initial velocity has a component along the x direction and an initial velocity along the y direction. Now, why would we want to do this? Why wouldn't we want to take our axes and tilt them like this? Could I do that? I mean, is there something special about this and this versus this and that? They're both orthogonal axes. Why use this and this? Because gravity has a particular direction, right? We're assuming gravity goes this way. And if we can work with an axis where it aligns with, where there is, the acceleration aligns with one of the axes and not with the other, then there is no quadratic component in the x direction, and there's only gravity working in the y direction. And then you can think about them as behaving independently. Whereas if I went to a coordinate system that was rotated like that, then I'd have to worry about a gravitational component along this axis and a gravitational component along that axis. That just makes my life harder. Okay, so we're doing this simply because it's the easiest way of doing things. So some physicist long ago wanted to make his life as easy as he could, and then we follow that by convention. But sometimes we don't say why, but it's mostly all of the things we do in physics are because that's the easiest way that people figured out how to solve them. Okay, so now if I look at simply the strength of the projectile motion along the x-axis and the component along the y-axis, what I'm really interested in is finding what V0x is. What is V0x in terms of V0? If I know the angle here, theta, what is V0x? And by writing it like this, I'm just saying that this is a magnitude. Yeah. Okay, good. So I have V0 cosine of theta, and V0y is V0 sine of theta. And that's the notation that we're going to be using. So V0 is just going to be V0 cosine of theta I hat plus V0 sine of theta j hat. equations that we learned in one-dimensional motion apply, but we have to consider one-dimensional motion along the x-axis and one-dimensional motion along the y-axis, and treat them differently, because there is no acceleration along the x-axis where there is along the y-axis. So if you recall those equations of motion, so first let's consider what happens along the x-axis. As we said, there is no acceleration along this direction. We're going to be ignoring any forces that are acting on the particle in the x-axis. And so we see that x, what we'll call it is x minus x0 is just going to be simply v0x times t, which we say is v0 cosine theta times t. Okay, so as a function of time, what we see is that it undergoes a constant velocity proportional to the component of the velocity in the x-axis times the time. And you can see that this is linear in time, which means that it does not, the velocity does not change with time. The second thing I want you to note is that we assume x0 is equal to 0. And that's simply just because of the fact that we're assuming that we launch the projectile from the origin. In the coordinate system that we've chosen, we say that the 0 of the coordinate system is at the origin, and that's where we're choosing to launch the projectile. So that means that we can just say x is equal to v0 cosine theta t. And y minus y0 is equal to v0y times t minus 1/2 g t squared, where now what we've assumed is that we have an acceleration that's pointing downward, okay, and that the acceleration is g. Okay. And so we get that this is v0 sine theta times t minus 1/2 g t squared. So that is our direction here, and we're also going to assume once again that y0 is equal to 0, because we're assuming that the origin is where the projectile is launched. Okay, we have another equation of motion that we, as you remember last time, that's independent of t, because we solved for t in the two equations, and we got something looks like v squared is equal to v0 y squared minus 2g y minus y0. Correct? Okay, so then this is, as you recall, v0 sine theta squared minus 2g, and then we're just going to assume y because y0, we've assumed v0. Sorry about the coughs there. So now if we look at the trajectory, what we're interested in is seeing what is this particle doing as a function of time? As I put in the parameter time, what is happening to the particle here? Now, what I really want to say is, okay, so x, these are like what are referred to as parametric plots. As a function of t, I want to see what happens to x and y. Right? We were doing this a little bit earlier. I said time t equals 0. I plotted my y position, and I plotted my x position. At time t equals 1, time t equals 2, time t equals 3. I want to be able to see what happens to y as a function of x. And so what we're going to do is we're going to get y as a function of x, and then look at the trajectory, and we're going to see that it has a parabolic structure to it. y with respect to x. So we're going to assume x is the independent variable and y is the dependent variable. So how do we go about doing that? Basically what we have is x is a function of t from all these equations, and we have y as a function of t from all these equations. So we want to solve for t, and once we have solved for t, then we can put that in for both. We can solve for t here, and then we can apply it into here, and then we'll get y as a function of x. So in this particular case, what we see is that t, we can use this equation right here. We've assumed x0 is equal to 0, and so we see that x is equal to b0 cosine theta times t. So we see that t is going to be equal to x over b0 cosine theta. Now, we have this function right here, and we're going to assume y0 is equal to 0 again because we've launched it from the origin. And so y, and then we're going to plug in t that we found earlier here into here and see what we get. So we get y is equal to b0 sine theta. Then we put in x all over b0 cosine theta minus 1/2 g, and then we have x all over b0 cosine theta squared. So these b0's cancel, and we get a sine theta over cosine theta, which is a tangent of theta. So we see that we get tangent of theta times x minus 1/2 g, and then we're going to get an x squared all over b0 squared cosine squared of theta. So, looking at this, so what is a parabola? If I were to draw a parabola, what do I get? Yeah. Would you raise your hand? Okay. What is, how do you draw a parabola? What's the functional form of a parabola? Yeah. X squared, something with x squared, some coefficient of x squared. Okay, so this is where we get the x squared. Now, if this term wasn't here, what would this look like? Yeah. Okay, so this would look like a, right? You can just think of this as a coefficient. This is just a constant, right? This is a constant, this is a constant. And that just basically defines a curvature associated with that parabola. Right? So what I would have, but it would look something like this, right? When x equals 0, y is equal to 0. What I'm drawing here is ignoring this. So what does this term do? To the parabola. Yeah. Okay. What it's going to do is it's going to lift it up. Right. We're going to, in this particular case, this parabolic function, what it does is it allows us to get something that looks like what we normally associate with classical motion. Right. If I toss a ball, then it's going to have that classical that parabolic free fall trajectory. Okay. All right. Okay. So anyway, what you can see happens here is that this gives us this parabolic trajectory. This allows us to get this gives us the initial kind of what looks like the initial information about the system. And this kind of defines a curvature. So now let's do one last thing, which is finding the range. And then we're going to do some experiments. Okay, so what the range is a very nice way of calculating how far something is going to go if you know its initial velocity and you know its angle of its trajectory. But the range assumes that what you're doing is you're saying, I'm going to start at some initial point 0, and that the final height is the same as the initial height. Okay? Range. So y final is equal to y initial, which is equal to 0. Okay? So the range is simply what is the distance that the particle will have traveled along the x-axis after the particle has gone from its initial height back down to its that same height. Okay? So we just use two equations. One is r is equal to v0 cosine theta times t. That's just simply the x displacement. So we're looking at the distance along the x-axis times v0 cosine t. And we know that the final height, y, is equal to v0 sine theta times t minus 1/2 g t squared. So all we've done is we've assumed, oops, no, we don't need to keep this v0y. This needs to be v0 sine theta times t. That's probably pretty hard to see that. Chalk is behaving not so desirably. Okay, so what will we do? Once we have, again, we have this parametric type of system. So we need to solve for t here, substitute it in for here, and then write everything in terms of the range. So we're going to do a little bit of algebra here. So if I look at this, I say, from this equation, I see that t is equal to r v0 cosine theta. And then I'm going to put it back up into here. So I have 0 is equal to v0 v0 sine theta, and then I'm going to put in the t here, which is what we just wrote down there, r. Better. Okay, so v0 cosine theta minus 1/2 g, and then we're going to put in this r over v0 cosine theta squared. Now that's easy to solve, right? We bring this to one side, we keep this over here, and then the first thing, okay, so we have v0 sine, we can get rid of the v0, these v0s cancel. The next thing that's, well, I'll do that. Okay, so sine theta over cosine theta, and I'm not going to make this into tangent of theta, and you'll see why in just a minute. Times r is equal to 1/2 g, and then we're going to get an r squared all over v0 squared cosine squared theta. So one of the r's cancels. So we just have r on this side. And one of this cosine theta and one of the cosine thetas cancel here. So what we can see is if we bring this term up to here, right, we get a b0 squared and we get a, so if we just do some algebra, we get 2 up here over g, and then we get a b squared in the numerator and a cosine theta in the numerator. So we see that r is equal to 2 b0 squared sine theta cosine theta all over g. But what is the sine of theta times the cosine of theta? Right, it's the half of the sine of 2 theta, right? And so we can just take 2 sine theta, cosine theta, and that's equal to sine of 2 theta. It's one of those trigonometric identities that I hope you're familiar with at least. That 2 sine theta cosine theta is equal to the sine of theta plus theta, which is just the sine of 2 theta. So we get that this is equal to b0 squared all over g sine of 2 theta. Now there's something really interesting here. At least I hope you. So what this says is the range is b0 squared over g sine of 2 theta. What is the maximum range there that you can then get? 45 degrees. Is that interesting? So why do you hit a golf ball with the driver with, say, a 10 degree? We're saying that the maximum distance you can get is 45 degrees. Yeah. Okay, so there's a rolling component to it. Air resistance, right? What we've assumed so far is that this is an air resistance environment, right? But with the air resistance, it's actually going to, you have to change things down. The optimal angle then becomes lower because you want to put more of a component into the X than you would normally. But in the absence of wind resistance, you need this. And I don't actually know what the angle of the driver is. It's like 7 or 10 degrees. Anyone know? Anyone recall? Okay. So I think it's somewhere between 7 and 10 degrees. So if I simply just put in 2 times 45, 2 times 45 gives me 90. Sine of 90 is unity. And so I see that the range is equal to b0 squared. The maximum range is just b0 squared over g. Well, this is kind of neat, right? Because now I could say, if I know how far something goes in a wind resistance, in an environment where there's no wind resistance, then I can know what v0 is. And I can actually compute how fast the projectile is going based upon the range if I set the angle right. Now, what's a situation in which I would have very little wind resistance? What's a good situation? Okay, vacuum, good. Anything else that you can think of? Yeah.
Out of the atmosphere.
Okay, so if you're in space. Okay, good. Anything else? What if you're stuck with working with air? What would be a good, a relatively good approximation of being of not having wind resistance? Something's moving slowly. Okay? Something's moving slowly, or something is very, very dense. So imagine that I throw a bowling ball, a fairly slow, I toss a bowling ball. You might as well ignore wind resistance unless that bowling ball is going 200 miles an hour. Right? It doesn't. The density is so high that the wind resistance isn't going to be changing things very much. So if things are moving slowly, or if the projectile is very, very dense with respect to the air and moving relatively slowly, then this is a pretty good approximation to what actually happens. Okay, so any questions? All right, so now we have a little experiment for you all. Okay, so my trusted assistant. Oh, I hear that. So what's going to happen here is we're going to, I think the medium range does work. So what do you suppose is going to happen here? What's going to happen as soon as this ball passes through this exit, it's going to trip a laser beam, which is going to have a sensor that's going to release the magnet that's holding that monkey, I think it is, whatever that creature is. And the ball is going to then undergo a parabolic free fall trajectory here. What do you suppose is, where do you suppose the ball and the monkey are going to be relative to each other? I got it. Now, I'm going to put it on a higher speed. So that was a medium range, and you saw that it hit the monkey when it was pretty far down. Okay, now I have actually got it at a, instead of being a medium range, this is a long range. In other words, this is a much higher, a much faster trajectory than what is supposed to happen. It's going to hit the monkey but higher up,